of this first edition of Planck. So we have scheduled 3 talks for this session, but there will actually be a 4th. The second talk from the first selected talk session from the morning has been moved to the very end of this session. It'll just be a 10-minute talk, so instead of ending at 5:50, we'll end at 6:10 or something like that. So to kick us off, we have Alex McCaskey, who's going to tell us about their work in extending modern C++ for heterogeneous quantum classical computing.
Thank you. Yes, my name is Alex McCaskey. I am a staff scientist at Oak Ridge National Lab. I'm in the Computer Science and Mathematics Division. I serve as the Systems and Software Lead for the Quantum Computing Institute at the lab. And so what I'm going to do today is kind of share with you maybe like the DOE perspective, the Department of Energy's perspective on near-term quantum computation, how we see it fitting into our existing kind of heterogeneous computing model, but then also talk about where we're moving toward this kind of single-source programming model for heterogeneous quantum classical computing, and specifically extending C++ for that. I'd like to, like I said, talk about what our requirements are. What do we need in DOE scientific computing for a future, quantum-enhanced architecture that one might envision. I'm going to give a little bit of background on a framework that I've been the PI on for about 3.5 years. It's a project called XICC. I'm just going to touch briefly on it because it kind of serves as a foundational software layer that we've built what I'm primarily talking about for this talk, this QCore compiler on. So QCore, unoriginally called Quantum Compiler from Oak Ridge, we call it QCore. I'm going to delve into the language extension specification that QCore provides. This talks about what does the programming model look like, what does the execution model look like, what are some of the data types that we provide as part of a runtime library implementation of this extension. I'll talk about the core implementation itself. This is kind of where I've been leading this work at Oak Ridge National Lab. And we've leveraged the Clang and LLVM infrastructure for this. So I'll talk about that. And then we have some recent developments I'd like to touch on that kind of streamline the work that we've done so far. And I'll talk on that as well. Let's see. Okay, so quantum computing, quantum programming at Oak Ridge National Lab. We have this Quantum Computing Institute, which kind of brings together a number of different fields to talk about how do we advance the state of the art in quantum computing. Oak Ridge National Lab is perennially one of the hosts of the fastest supercomputer in the world. Right now we have Summit, something like 4,000 nodes with 6 GPUs attached to each node. We are heavily invested in this accelerated node model of computation. And so a lot of our quantum programming and quantum computing thought processes kind of focus on that accelerated node computing, which a lot of people are thinking about, I believe. We borrow from some of these existing CPU, GPU models that have come up in the past and that are used heavily today. And we wonder, we know we have Summit now. We're planning, Frontier currently, which will be the exascale machine housed at Oak Ridge National Lab in the next couple years. What would a future post-exascale machine look like if you were able to enhance that architecture with one or many available quantum processing units? I hope that happens by the time I retire, but we're working toward that each day, obviously. So if we're thinking about these types of models, we need to focus on system-level software infrastructures that integrate with existing programming models, existing tools, existing compilers, existing parallel runtimes. So this is a heavy feature that we bake into a lot of the work that we do. In the past few years, we've had heavy investment from DOE with regards to quantum computing. So we've had this Quantum Testbed Pathfinder project, which at Oak Ridge, we're really focused on what does it mean to benchmark high-level applications against currently available quantum computers. This means that we want our software infrastructures, our programming models to be obviously hardware agnostic. We want to be able to write once, run anywhere. We've also got investments from Quantum Algorithms project from the DOE Oscar program. This is really focused on enabling hybrid quantum classical algorithms for scientific computing tasks that DOE is interested in. So quantum field theory, nuclear physics, quantum chemistry, you name it. We're working on hybrid algorithms that kind of enable or start to think about how would you enhance the state of the art in some of these fields. And of course, for that, we want to be able to extend ourselves for domain-specific languages. So being able to come up with embedded DSLs in C++ or other standalone languages and tools that enable us to express these types of problems and then efficiently map them onto the quantum architecture that we're targeting. So I've named a few of these features. We basically started most of this with this XICC work, which has provided a hardware-agnostic, system-level infrastructure for quantum computing that is also extensible for DSLs. It is not single source, though. A lot of the work that we do with GPU, CPU programming models is single source in C++ or Fortran. XICC basically takes the programming approach of saying, hey, here's a quantum kernel source string, just as a string in the native language in C++, for instance, and pass it through some API for compilation, okay? And so the QCore work builds off of this infrastructure, but provides that actual language extension that lets us define and implement a quantum classical C++ compiler that gives us that single source programming model. Okay, so XICC, completely open source. Anybody can go check it out under github.com, Eclipse XICC. It is the system level software infrastructure. It's in C++. We have Python bindings. It's completely modular and extensible. It builds off of this kind of like plug-in model for injecting new implementations for various interfaces that are defined by the framework. The architecture at a high level looks like this, where we decompose it like you would see in any classical compiler textbook, with a front end that maps languages to some intermediate representation, some middle end that defines that intermediate representation, plus optimizations and transformations on it, and then obviously a back end that lets us take that IR and map it to any available architecture that we have implementations for. And as of right now, I can say we have implementations for all the IBM backends, all the IBM simulators, all the Rigetti backends, all the Rigetti simulators, IonQ, D-Wave, and we also have a very large scale, Summit scale tensor network simulator for large circuits. And the goal here is basically just to provide this foundational infrastructure to build tools and compilers on top of. Okay, here's a quick code snippet of just the lowest level base API, just so you get an understanding of what it looks like at the foundational layer. You know, users say, give me an accelerator. We call backends accelerators in XICC. You specify which one. This can be Rigetti. This can be, IBM, whatever. You specify a front-end compiler. This is asking for this XASM compiler, XICC assembly compiler that we've defined. We have some ANTLR grammar and ANTLR parser for this language. And then you just write one of these quantum kernel expressions, which is just a C-like function with a function body composed of quantum instructions. And you can go to any level of abstraction here. This is at kind of the lowest assembly level, but we have compilers for DSLs and things like this. You compile this with your compiler implementation. You get the IR. You can do optimizations, transformations on it, and then you can loop over that IR instance, evaluate at concrete angles for like a VQE instance, for instance, or a VQE algorithm, for instance, execute on the back end, get results, all this kind of stuff. Okay, so the QCore specification, the idea here is to provide finally this single source programming model in C++ so that we promote familiarity for our existing computational scientists who are writing these applications on some of these large-scale architectures, and enable us to integrate quantum accelerators, quantum coprocessors with existing tools and techniques. So this is kind of how we decompose the target machine model for this entire heterogeneous architecture. So we don't limit ourselves to any, just one CPU. We say, let's imagine we could have one to many CPUs. We have, a number of accelerators here, and we just treat the QPU like an accelerator in this model, okay? We assume some classical control system that drives pulse-level execution on the hardware, and we assume some shared memory system so that we can get bit strings and results back from the hardware. As of right now, the QCore Spec is primarily targeted at variational hybrid algorithms. So like your VQE type algorithms and things like that, Quawa, so, algorithms like that. It's technically not meant to be specifically for variational algorithms, but that's kind of where our work has kind of moved, since these are some of the near-term algorithms. It's NISQ ready. It's easy to integrate error mitigation strategies. I'll talk about that. And we've tried to keep this execution model asynchronous. You launch these tasks on the attached coprocessor, you go do other work, and you sync back later when you're ready. You can check out the QCore Spec paper here. These are all at the end of the talk as well. So just to give you a view of what these prototypical variational problems look like for us, and in general, really, and then how we decompose these tasks into data structures in the model itself, okay? So for a given VQE or variational type run, we consider some parameterized unitary, some state preparation step. Okay, we call this a quantum kernel in the QCore spec. We consider some general observable, and observables basically provide a mechanism for taking in an ansatz, a parameterized state preparation circuit, and appending measures to it. Okay, so you have some Hamiltonian representation of the system, and you want to, for a given Pauli term in that Hamiltonian, for instance, append measurements that change rotation to, or change basis to the z basis and make a measurement in these types of things. So you give one kernel into the observable, it spits out many kernels that are measured. We have a concept of the optimizer itself, so when you're going through this kind of iterative approach, we want to keep ourselves general for any type of classical optimization routines. And then, of course, an objective function. So this whole green box here we consider like an objective function. Given a set of parameters plus some pre and post processing on the quantum execution for the back end, give me a result, okay? Okay, so the execution model is very simple. We have defined in QCore a task initiate method or function, and we have several overloads for this function. So by default, task initiate can take the parameterized ansatz, the objective function, the observable, the optimizer, and any parameters like initial params or things like this, and execute an asynchronous task solving that problem or minimizing with respect to that objective function, okay? But then we have variants, so like, if you don't give us if you don't give us an objective function, we assume it's just the expectation value with respect to z, and all sorts of other defaults here. Task initiate returns what we call a handle. This is basically just an implementation of the standard future promise pattern. You say handle.get, you get actual results back containing all measured bit strings and execution metadata. Okay, so implementing this spec, we decided to implement this in C++. What do we have to do that? We have to extend C++ with support for these quantum kernel expressions. When we kind of, for the first initial pass here, targeted just standard C++ 11 lambdas, okay? We want to integrate XICC with Clang plugins, and then we want to implement these data types that I just mentioned, and of course, task initiate, okay? Okay, so what's the Clang work that went in here? We didn't want to fork Clang. We didn't want to fork LLVM. We don't want to be maintainers of a fork of those large code bases. We want to contribute plugins to Clang, okay? And there's a number of plugin interfaces that exist, specifically this AST visitor interface that you can implement. And also this external same source guy became pretty critical for us as well. I'll talk about these in a sec, but there's some of these core like data structures within Clang that you have as an external developer have access to that lets you modify the abstract syntax tree, do analysis on it, and rewrite source buffers with this rewriter, okay? And so our goal is to be able to say, hey, here's a lambda that has quantum code in it, and we want to be able to map it to something that is actually just API calls to XICC, okay? So the workflow looks like this. A standard C++ file containing both classical and quantum code comes in. You run the QCore compiler on this file, which basically kicks off the typical Clang workflow where you start to generate the abstract syntax tree. If Clang does not know what a symbol or instruction is, it, as a last resort, kicks to this external same source. We implement this guy to say, hey, this symbol, I know it's a valid XICC instruction, I can parse it, and I'll return you an empty function decal, okay? And we just do this for every instruction, every unknown instruction that's seen. We now have a valid AST. We run a recursive AST visitor on that AST that looks for lambda expressions, looks for the actual nodes in the tree that are the lambdas themselves. We can take the lexer and the preprocessor and the source manager that Clang provides and get that code as a separate source string, and then you can just go through the existing XICC compilation workflow. And this is where all the quantum compiler hooks happen. So quantum optimization, placement on the hardware with respect to connectivity, even noise-aware placement with respect to like the noise model that comes off of the hardware, things like this. So now we have this modified, we've compiled this quantum code. We can update the source file itself with this rewriter routine, and we just output a hidden test.cpp file, okay? And we just compile with any classical compiler to get a standard binary, standard object file, okay? So the runtime library, I've basically talked about all this. We have implementations for observable, for Pauli observables, fermionic, chemistry, all sorts of stuff. You can say, I have a basis set that's this, and here's my molecular geometry, and we'll give you back a Hamiltonian, an observable. We have optimizers that are based on NLOpt, MLPAC, SciPy, all sorts of stuff. And we have built-in objective functions for VQE, some machine learning stuff, some circuit structure learning and parameter optimization algorithms as well. Task initiate, we just leverage standard C++ async in future. And then, of course, we configure up execution on the back end with XICC. And so, like I said, this gives us all sorts of backends. Okay. For error mitigation, this kind of falls back to XICC. We have a standard, obviously, an accelerator interface that we back in with IBM and Rigetti and all this stuff. But we define a decorator interface as well that is itself an accelerator, but also contains an instance of an accelerator. So it's this common decorator pattern, all right? And this gives you an opportunity to say, hey, I want the IBM accelerator decorated with readout error mitigation. And all the user sees is an accelerator, and all they see is execute. And this gives us an opportunity to do pre-processing, execution, post-processing, which is really good for a lot of common error mitigation strategies. All right, so you've basically seen all this. This is kind of just showing it all together. If you want to do like VQE for computing the Deuteron binding energy, this is kind of one of our prototypical hello worlds. Define your quantum onsets, your parameterized circuit as a lambda, get an optimizer, get an observable, initiate the task. This is asynchronous, go do other work, come back later and get the results. Compilation is very simple. This is all masking Clang calls and actually providing the header files that we need for you. You don't have to worry about any of this stuff. You can add header files to these lines, and you can add link line and all this type of stuff. But you just run QCore and specify the backend QPU. It can be, the accelerator, the backend for the accelerator. You can decorate it with error mitigation, all sorts of stuff. All right, so now where are we going with this? The workflow that I just described is pretty complicated. We'd like to simplify that. We have a new project from DOE, this ArcQC project, where we have more people working on this. And we have actually Clang developers working on this now, which is really cool. So what we're going to do, what we've done in the last few weeks actually, is define a new plugin interface to Clang called Syntax Handler, okay? Syntax Handler has a name, okay? And this name correlates to a function attribute that the user itself, or the user, him or, he or she puts on the function itself. I'll show you an example of that. But you implement this get replacement. We give you the tokens for that function, and you can write new code to an output stream based on those tokens, okay? Let me show you this. So for quantum computing, we've implemented this syntax handler. You just annotate your function now. Say, I want you to use the syntax handler that's corresponding to this XASM language that comes from XICC. We're given these tokens by Clang, okay? And now we have an opportunity to analyze them, aka map them to a kernel source string for XICC, push them to the corresponding XICC compiler, get IR, do whatever we want with that, optimize, placement, all this type of stuff, and then rewrite these tokens to be something like this, right? Just API calls, that's it. So, and you could do this just in time, like I'm doing here, or you could do it ahead of time. You could, if the circuit itself didn't have any runtime parameters that we didn't know at compile time, we could do all this stuff ahead of time and compile to an actual quantum classical binary that had already affected quantum compilation, okay? And then running this, we're gonna obviously bake this into QCore, but if you just want to manually run this with Clang, you would specify the plugin, so that the plugin would be loaded and the syntax handler would do its stuff and all that kind of stuff. So the user just sees, hey, give me 2 qubits. I've defined this function. It's a Bell state. Oh, and I've put 3 C0s. I should only have 1. This will be optimized away. And they just run the function, right? And then you get counts back and you can do whatever you want. Okay, so thank you. And I just wanted to point out that, like I said, all this stuff is open source. QCore is up here at this repository. We have a new XICC publication up. And the QCore Spec, we're coming out with a paper about the implementation itself, but we've got a paper up for the QCore Spec. Here's my email, and here's funding acknowledgement. So thank you.
Any questions?
So could you give me some special consideration on intermediate representation?
Oh, just talk about it a little bit more.
Yeah.
So basically, in XICC, we define 3 core interfaces. We define an instruction interface, we define a composite instruction interface, and we define the IR itself. So the instruction we implement for just basic digital gates. We implement it for pulses as well. We implement it for D-wave instructions, so D-wave analog, like we kind of decompose qubit biases and couplers into as instructions. Composite instruction contains further instructions and is itself an instruction. So you get this kind of like tree-like pattern, right?
So is there
Yeah.
any special consideration on optimization? So just
Yeah.
so your solution maybe is just emulate the matrix computation on CPU GPU.
No, we don't store any matrix information about the instructions themselves. So for optimization of the IR, we have defined an IR transformation interface, which basically takes as input the composite instruction that you want to optimize and the hardware that you're optimizing to, okay? And so you have, with the hardware, you have connectivity information, you have noise models, you have things like this that influence the optimization strategy that you're implementing for that IR transformation.
So why don't we take more of the details
Yeah, we can talk
offline?
after this. Yeah, definitely.
We're running a little bit behind, so I'd like to move on to the next speaker. So thanks so much, Alex.
Thank you.